and I have tried to get something a little bit more interesting to work, but it hasn't quite got there. So if you're willing to bear with me, you might see me flap around a bit. If you've never programmed in Rust, that's totally fine. You can think of this as an introductory tutorial. I'll try and take things relatively slow. If you don't know what the Mandelbrot set is, that's okay. We'll try and figure that out together as well. And let's make some pretty pictures, or at least let's try to make some pretty pictures. Cool. So, yeah. So undoubtedly, if you're into the computer scene at all, you would have seen this really iconic picture of this fractal. And it turns out that one of the reasons why you've seen it so often is that the mathematics behind it are ridiculously simple and ridiculously fascinating. We are going to try to start with something that looks a little bit more like this picture here. So this guy, I say guy in the gender neutral sense, is what we're trying to emulate right now. This is what I know I can definitely produce in the next 20 minutes or so, maybe even sooner. And where I would like to get to, though, is providing you the skills to be able to kind of create these amazing visualizations. Turns out that if you zoom in, and we'll discuss what zooming in means as we go, you'll be able to kind of like explore this pattern for the rest of your life. Yeah, so big ask. Right, so now I've got a whole bunch of code up on the screen, and I just kind of we'll demonstrate by we'll actually start with it working. So I'm compiling some code, I'm compiling more code, and boom, I've got something that looks a little bit like that text diagram, and I can actually change the way that it looks by altering these parameters. So if I want a kind of a more zoomed out view, I'll just increase all of these by 10. It might not look particularly attractive because we don't have a great deal of resolution. We've only got 120 by 20 pixels. So I might see if I can double that one, or maybe see if we can get a few more pixels on the other side. And we'll run it again. Oh, we're all the way over here. That was weird. Oh, right, so what I should have done was this one needs to be about 10. So what? I don't know if it's obvious, but I'm shifting within the Mandelbrot set. I'm shifting kind of my viewport. So we're only seeing a very, I'll try and, how do I do it? So if I select this stuff here, that is only, it's far to the left. We're actually missing out a whole bunch of the set that we care about. The most interesting set, that really classic diagram, is visible within about -2.5 and 1.5, and then same with the Y. It's a little bit less constrained. Okay, so if I rerun this, all right, okay. So we're actually very, very zoomed out, and this is the render. Now, we don't have a great deal of detail at all. But what I'm trying to demonstrate is that you can play with the parameters and change your output, and change what you actually get to see. And that means that you can have a whole bunch of fun with the renders. In particular, if you go from just printing things out onto the terminal onto a frame buffer, and like you can create sliders to kind of move things around and zoom in and out and create videos. Can you zoom in your editor term, old eyes, etc., etc.? Okay, right. Yep, apologies. yeah, also not just old eyes, but also like the internet streaming. So I'm never sure if it is super useful. Yeah, and unfortunately, I've got a whole bunch of real estate on the right that I don't need. I'm gonna split it. Anyway, so what we're trying to change here, we've got 4 parameters that I've been playing with. It's a bounding box if you're of the x values, the minimum there, and the y values up and down, left and right, up and down. And these 2 parameters down here, which are integers, are the number of pixels or the number of characters that I'm printing to the screen. Okay. Let's kind of dig into how we create this thing. So I'm going to get everything out of the way. I'm going to try and hide this as well. What I want to focus on is Mandelbrot at point. So what we can think about is that if where we start is that at every single time we are printing something to the screen, like every character that we see, we actually calculate this function. The reason why the Mandelbrot set is kind of weird is because it uses complex numbers rather than real numbers. You can think of a complex number as, instead of existing along the number line, it also exists in like the number plane. So the imaginary part, which is kind of the worst word to use for that at all. Like, I've got real numbers here, and imaginary numbers actually represent the kind of the y-axis along the number line. So we know the number line from when we started primary school. We start at 0 and we kind of move into infinity. Well, the imaginary part is kind of going to go up. A number that is inside an imaginary number is also known as a complex number. Now, Rust doesn't include complex numbers itself. It pulls in, so we can pull in through the num crate a complex number implementation. It fits the same space. So Rust programmers are always concerned about space. Like, what does it look like in memory? And what we see here is that the memory layout is compatible with an array of type 2. So this enables us to put in other scalar values. We're using float 64, but we could put in float 32. We could put in whatever we want. So that's a bit strange. Oh, so it's trying to demonstrate that you can't use these directly from C. You need to have a pointer to the array, but I find that's kind of an esoteric kind of use case. The way that we can construct them is via the new method. Alternatively, if you're feeling fun, I suppose, you can give yourself a little bit more of a descriptive, self-describing code. You can use the literal syntax to create the struct. So RE stands for the real part, and IM stands for imaginary. So what on earth is happening to calculate the Mandelbrot set? It's an iterative function. So what we do is we iterate through until we find some condition, and then all we're actually reporting back is the number of iterations it took to hit the condition. This condition is described in the literature as escaping. And when I say it escapes, what I mean is that at this xy coordinate, so remember that this function Mandelbrot at point is being called at every single pixel value in the space that we are concerned about. Now, for every single one of those pixels, we try and check whether or not this pixel represents something that's inside the set or not. And the way to calculate it is this thing here is like the z value. Cx and cy, by the way, represent the pixel itself inside or as a complex number. So we've got C. C is kind of a sort of a, I guess it's a constant in this regard. And we've got the Z thing, or Z. And what on earth is norm? Well, actually, let's worry about norm in just a second. First, we're going to look into this step that happens for as many times as we want. If we increase the iteration count, like the maximum number of iterations that we're willing to give it, that takes more time to compute, but we get a prettier picture, potentially. Excuse me. So we kind of, by the way, this grayed out type is generated from VS Code itself. So it's not actually in there. We could include the type definition, but this is the editor trying to be helpful to us. Now, if you've not used Rust, usize sounds like a strange type. It is the type of an unsigned integer in the width that is most familiar to your CPU. It's the size of a pointer, as if you've ever used pointers before. What is our check to see whether or not we've escaped, and we know like this point value is no longer within the Mandelbrot set, is whether or not the vector between the origin and the place that this number exists inside the complex plane is over 2. So another way of doing this is to say it's Pythagorean. It's just sorry if the trigonometry or so forth is a bit obscure. So, but we can also just say if the real part of the struct is greater than 2. This is the easy to calculate, but kind of mathematically impure. Like it's an approximation for what's happening. It's not very satisfying intellectually, I suppose. Which has changed the condition just to kind of provide a little bit more normality if you've never used complex numbers before. Because I'm talking about vectors and origins. The origin is just the 0, 0 vector. So the Z thing starts in the origin, and it's just how far has it drifted away as it goes through a series of transformations. Right. So an approximation is that greater than 2, or is the imaginary part greater than 2? It's kinda sorta the same thing. It turns out if you want to be even more specific, you could say that, is the square root of the, because it's Pythagorean, is the square root of the sum of those, the square of those greater than 4. And the reason why I don't really care about it, and this 2 is just kind of a magic number that people seem to use when they calculate the Mandelbrot set. Okay, so we've kind of dealt with this function to death. We've just had several other people join the stream, so I'm just going to show the magic again. Right, so what we do end up with is this thing in plain text that looks roughly approximately what we're used to. We can also do some other fun things if you ever are curious. So that actually almost looks prettier than this. So we can change the condition. I hit a whole bunch of rows for me. I'll rerun it. Okay, so this is you can see the difference in the render, that you can use the cheap a bit nasty. Or this one apparently, this one is supposed to be much using the distance from the origin, or the absolute value of the complex number is mathematically more pleasing. But actually I thought aesthetically the cheaper condition was kind of more interesting, just because it kind of looked way more jagged, even at this very low resolution. By the way, if anyone has any questions, do ask them in the chat. I know it's kind of awkward if you've never done streaming before or what have you, and probably means you have to sign up for an account. There are some other channels as well that I'm monitoring. So I'm monitoring the Twitch thing. And if I get kind of an odd tweet, you're also perfectly entitled to tweet me. I wouldn't recommend sending me an email right now. I'm not checking my mail. But definitely those two. Right, so we're kind of getting into the hard stuff. Am I? Or should I do? Yeah. Oh, let's kind of dig into this guy. So I've got three functions here. This is how it looks really ugly and disgusting. So bear with me. I've got this calculate Mandelbrot function with a whole bunch of parameters because, as it happens, I am going to be injecting this example into chapter 2 of my book, and I haven't introduced structures yet. So in that second chapter, so I've only introduced numbers. This is kind of my yeah. I would have a trial run because I finally got it working today. So anyway, so we've got all these parameters. These four here relate to the bounding box of the complex plane that we are interested in. These two are the output that we're producing. So the number of columns and the number of rows. Now those are obviously different, and we need to map between them. So to start with, we create, actually I might just for this, so if we take away the maximum value from the minimum, well, the minimum value from the maximum, we end up with the actual space that we are interested in within inside the Mandelbrot set. As it happens, this set width is going to be about 1. So I can just inject it where it's used down here. That might simplify some of the code potentially, because you have to have mentally one fewer variable. Or maybe it will make things more complicated because now you've got to do a whole bunch of more mathematics when you get down to it. So for every row, I need a better playlist, seriously. I think the problem, yeah, okay, so where have we got to? Sorry, I got distracted with changing the music. So this rows thing is the output, and so is row. So what we're doing is we're pushing output values to these two vectors that we've initialized as empty vectors, and then ask Rust to actually infer the type for us. So we get this really ugly type signature, vector of usize. Again, if you're new to Rust, usize just means an unsigned integer. Oh, goodness me. I am going to change the track. Not really a big fan of the dubstep, I would say. We can do something else. We could be explicit. So this is just for people who are relatively new to Rust. We can say we want a vector of vector usize with capacity. And width. This will have actually a slight advantage, and it won't be a bull, that should change itself pretty soon. This will have the advantage that we only make one memory allocation at a given time. And this one down here is different. It's whereas if we use kind of the common approach to well, this is kind of super easy syntax for creating a vector, we end up with several allocations. And so again, if you're into Rust, you start caring about when you're asking for memory, and you would prefer, if you could, to only allocate when you're able. I'm a little bit concerned that it's telling me that it's in, but I think it's just the type checker. I think it's just a little bit. I'm just going to double check that I haven't made a huge error by rerunning. I'll change the picture, make it a bit bigger maybe, and I might see if I can get a little bit more, increase the resolution just slightly. No, we've killed it. Okay, so right, so I've just made a syntax error. That's kind of awkward. So I need to actually say that the type I'll explain what on earth I've done and how I fixed it once I've confirmed that I fixed it. But why I need those two columns in there. I don't know if you noticed, but that run actually took quite a bit longer. We're asking for a lot more compute. As we increase the resolution by increasing the number of rows and the number of columns, the computer has to do a lot more work. By the way, would it be helpful if I create a GitHub gist of this, or bring it up in the playground even? The playground will render these because it's using one of the very common crates. This way people can kind of play around themselves. Share. Okay. Copy link location. So this is the link to the code that I'm running right now. If you click on the browser, you'll be able to kind of modify that to your heart's content as I go along. Okay, so we went back, we've got to go and talk about some Rust stuff. So why... so this syntax here might be more familiar. What this is a static method for the type vec, or at least kind of in some sense the abstract type, because Rust needs to be told, I think, maybe it doesn't, that what the vector is actually going to contain. It looks like it can actually guess, which is smarter than I anticipated. Oh, okay, right. So the Rust compiler is better than I am. We can probably align that one too. So how? So the Rust compiler knows that if I call the static method with capacity with height, it can infer the type for me. So that's useful. I didn't need that syntax error there at all. Okay. Now, the one issue that I really hate with Rust, he says, as someone who's trying to promote the language, is that it's really, really picky about numeric types. Everything needs to be like cast specifically. So the reason why I've got I've got 4 kind of shadow variables with trailing underscores that are yeah, I'm sorry, no more turbofish. Yeah, I'm sorry. I quite like the turbofish. I think it's cute. Alright, we'll just throw one back in there. There we go. there we go. I shouldn't get distracted. But I have been. Yeah, okay, so, so yeah, one thing is really picky. I've got to convert all of these things to floats, and it doesn't do it itself. Rust will refuse to do that because it is trying to give the programmer full control over what on earth the programmer is actually doing. Now, the reason why I need all these floats is because I need to calculate the percentage that I'm the percentage in kind of the number of which column I'm in and which row I'm in. See, that was the other way around. So, yeah, which row and which column I'm in both spaces. So I might be 30% through inside like pixel space and 30% through in the inside the Mandelbrot space, or inside this complex plane, which is rendered here. Now, values that are very what we do is kind of this nonsense here says that it just basically converts it. So from I'm iterating through the columns and rows in the pixel output, and then I'm creating a point that best represents that pixel inside the Mandelbrot space. And CX and CY, I'm just standing for complex X, like complex X and complex Y, and then passing that through to this Mandelbrot at point calculation, and then we get this value escaped at. So if a point escapes very quickly, that means that actually it doesn't exist within the Mandelbrot set. But if it stays there, it's definitely inside the set. And what's most interesting is the stuff at the borders, really, because that's where all the kind of the complexity lie, and that's why it's so interesting in terms of the chaos theory as well. So we don't have a good picture here because we've got, again, really low resolution, but the stuff at the borders is kind of where the magic is. And that's why people who are really interested in chaos theory, that's why they love it. So we're doing nothing with. So what we've got here is the iteration that it took to get out of bounds. Again, just for those people that have just joined us, we can play around with we calculate a. For every single pixel, we calculate this value, and we just kind of go through an iterated function where we just perform a bit of an update on some Z thing that relates to, and we kind of use the position that we're in as kind of an input to that transformation, and when it bounces out, we return. So, and we just say that once you've hit 2, and it bounced out. So this here is a value between 0 and 1000. I say 1000, what I actually mean is it is, which might be, you might be more further with using a variable name like max it is, or, you know, depending on your programming heritage, maybe something that looks a lot like that. So these are all values between 0 and 1000. 1000 comes from the fact that we specify 1000 in here. To translate the value to a character, all I need to do is go through each row and each column. I need to go row first and then column because the row corresponds to a to a line. So I can change that one into like a question mark if I want. And I would, encourage you to play with these. And we can change the output. I've got a whole bunch of question marks there.